Hello and welcome to this video on finding the domain and the range of a relation. And I'd like to preface this video by saying that this material that I'm going to go over, these examples, are more intended as an introductory video for more of a beginning or intermediate algebra student. So if you'd like to find a video that's that goes more in depth into the the concept of a relation between two sets, perhaps look up special tags on discrete mathematics or something other than beginning or intermediate algebra. Alright, so let's begin. Just got several examples here. So the first one, I've put up a video prior to this on understanding relations, and just recall from that, if you've watched that a relation, and I'll write it off to the side here again, a relation is just a correspondence between two sets of elements, two sets of things. They don't necessarily need to be numbers, as you can see in my picture here, but it's simply a correspondence sorry, that's a little tight there. It's a correspondence between two sets. Right. And one other note on some notation regarding relations. You might see little arrows like in my diagram here. This X and this Y are just elements of the two sets. So the set of, say, friends here, set of people, and the other set being the set of these birth dates, right? Just days of the year. And an arrow from one to the other indicates that X corresponds to Y, right? There's a relationship between this element and this element. So this would mean that X corresponds to Y, or you might see it written as Y depends on X. They sometimes refer to the second set as the dependent set and the first set as the independent set. But so the values in the second set depend on where they're coming from the first set. So or Y depends on X. So you might see this arrow notation, or as an ordered pair. So this X arrow Y, or the ordered pair with parentheses here and then X comma Y, mean the same thing. Okay, so both of these mean the same thing, that some element from this first set corresponds to some element from the second set. All right. And again, I went over all this in the video prior to this, called Understand Relations, if you'd like to take a look at that. Alright, so what we're asked to do, what I'm trying to do in this video, is state the domain and the range of the relationship, right, of this relation between this set of friends and this set of dates, birthdays. Alright, and so you can see the relationships. Max's birthday is November 8th, Alicia's is January 20th, Trent's is March 3rd, Yolanda's is November 8th also, like Max. Wanda's is July 6th, and Elvis's birthday, January 8th, right? So hopefully it's clear what the arrows mean. Again, this little notation here. That a certain person corresponds to a certain birth date. Now for some little definitions here. If you look at the notation, with the arrow notation or as an ordered pair, value from the first set corresponds to value from the second set. The domain of a relation is simply the set. So it's another set, it's another collection. Right? The set of all, you could say, the inputs in the relation. Right? So if I look at my arrow notation over here or my ordered pair notation, the first value in the ordered pair or the first value in this arrow notation are sometimes referred to as just the inputs, right? The input of that particular ordered pair. So the domain is the set of all, inputs of a relation, all the first values or first coordinates of the ordered pairs, or all the left values or first values in the arrow notation. So I've got the arrow notation going on up here in my this picture, by the way, is called a mapping, and you probably saw this in the previous video. A map or a mapping, and that's just one way to represent a relationship between two sets. There's mappings. You can write it as just a set of ordered pairs, as we'll see in the next example. You can make a graph of a relation if it's a relationship between two sets of numbers, which we'll see in our last examples. And in a future video, you'll also be able to write the relationship between two variables as an equation. Alright, so you have a mapping, a set of ordered pairs, a graph, or an equation. Right, those four representations of a relationship that we're going to be seeing examples of throughout my videos. Okay, so if the domain is the set of all the inputs in a relation, then the domain for this particular problem, this particular example, is, again, it is a set. So usually sets are written with these curly braces. Right, you can just draw a little S and a little backwards S connected at the middle there. And looking at my picture, all of the inputs, right, the left values in the arrow, or the left, if you were to write this as an ordered pair, you'd have the ordered pair with Max first, and then a comma, and then November 8th, or Alicia first, comma, January 20th. So all these values over here, all these names of people, the friends, are values that are considered, inputs in this relation. So these belong to the domain. So the domain of this relation is, consists of Max. Max is in there, right? Max is an input in one of these arrows, right? Alicia is an input, right? So Alicia belongs to the domain. Trent is also, right? Every single one of these friends, corresponds to some element in the birthday set. So any element in the friend set that corresponds to an element in the birthday set belongs to the domain. So every single one of these, Trent does, right? Yolanda does, comma, Wanda, and finally Elvis. And that's it, right? There's no other element of this friend set that corresponds to an element of the birthday set. No other inputs. So this is a set here, and then close the braces, close the set. So this set with these 6 people's names, 6 elements, would be considered the domain of this relation. Yeah, so I'm hoping that's easy to see. Alright, so that's the domain of a relation. the range of a relation is another set. All right, so it's the set of all the elements in the second set that depend on elements in the first set. Or they might just call these, and they're just going to call these, the outputs. The set of all outputs of a relation. Okay, so back over here, in my, in either my arrow notation or the ordered pair notation, when you say x, corresponds to y, or y depends on x, that y, that second value, so either the second coordinate in the ordered pair or the value on the right after the arrow, could be, if the first value is considered the input, they'll consider the second value the output. Right. So any value in the second set, this birthday set, that actually depends on something from the first set, the friend set. Any value over here that depends on something over here that is at the end of an arrow is an output. Is this guy over here, this second value, or in an ordered pair form would be the second coordinate. So it looks to me like, all 5 of these elements in the birthday set belong to the range, right? Every single one of them has an arrow going to it, right? Every single one of them depends on a value in the first set, the friends set. So that's it. So for this particular example, the range is, now again, it's a set, and again, so for a set we open it up with this curly braces, and I'm saying, January 20th is an output, right? January 20th does correspond to, or does depend on, a value from the friend set. So January 20 is in there, comma, March 3rd is an output, and you can see that at the end of an arrow, comma, July 6th is an output. It looks like, again, I said every single one of these is an output for some value in the friend set. Right? So July 6th, November 8th, and finally January 8th. Sorry, I'm going to push this down here just so I have room. And that's it, right? All 5 of these elements belong to this set, and I'll close the set with the curly braces. Again, a little backwards S, forwards S connected. And that's it. Very simple. Hopefully easy to see what is in the domain and range of a relation, especially when there's a mapping, right, where the arrows are very clear. And just because something is in the second set over here doesn't mean it's going to be in the range, right? Or if I had another date over here, say I put in June 5th or something, and there was no arrow going to it, then it wouldn't belong to the range, right? The range only consists of values in the second set that are actually dependent upon a value in the first set, that are actually at the end of an arrow, or that are actually the second value in some ordered pair. Alright, so just be careful with that. Great. Alright, so that was a mapping. Very easy to see the relationships. My next example, I'm going to be doing the same thing, is state the domain and the range of this relation. Now here's a relation that is represented as a set of ordered pairs. Okay, that's another way to represent a relationship between a set of numbers. Now these are all numbers here, not names and dates like the previous example. So here's a relationship, or a relation between one set of numbers and another set of numbers. Now if you want to, because there are only a finite number, a countable number here, very small number actually, only 4 of them. Because there's only 4 ordered pairs, if you wanted to, you could make a mapping, and I'll do that very quickly here. you could make a mapping for this where, in one box I'll put all the first coordinates. Right, we've got the numbers 1 is a first coordinate, 5, and I did this in the previous video too on understand relations, so if you want to see this done more slowly, you can go back and look at that video. So all the first coordinates, 1, 5, 8, and 10 in one box, so there's a set of numbers in this relation, and then all the second coordinates in another box, right, the elements that these first coordinates correspond to, and those are 3, 4, right, there's 3, 4, and no need to write 4 again, right, if you saw the last video as well. There's no need to repeat, you have 4 in the second set, this is just, 4 is in the second set, you don't need to write it again. And then 13, right, that last second coordinate. And then some arrows, right, some indicating the relationships. 1 corresponds to 3, or 3 depends on 1. So 1 corresponds to 3. Sorry, I know last time I used a ruler, but there's an arrow. I guess it doesn't really matter if it's perfectly straight. 5 corresponds to 4. 5 in the first set corresponds to 4 in the second set. 8 in the first set corresponds to 4 in the second set, so there again. And then 10 in the first set corresponds to 13 in the second set. So if you want to, right, you could always do this. You can always make a mapping. If there's just again a nice simple number, you're gonna see relations in the future. In fact, even later in this video, that have infinitely many ordered pairs. So there is no way you're going to be able to make a mapping or even do a set of ordered pairs, because if there are infinitely many of them, you can't possibly list them all. But for these ones with a finite number, a nice easy smaller number, going back and forth between a set of ordered pairs and a mapping to represent the same relationships is pretty simple. And then hopefully from this it's easy to see. Again, you probably didn't need to do the mapping to state what the domain and the range are, right? The domain of this relation is the set of all the inputs, right? All the first coordinates of the ordered pairs, or all the elements in one set that actually correspond to these elements in another set. So the 1, the 5, the 8, and the 10 all correspond to some element in the other set. So 1, 5, 8, and 10 make up the set of, that's called the domain, the set of the inputs. Okay, and the range is, again, just the set of those outputs, all the second coordinates, the 3, the 4, and the 13. Again, no need to write 4 twice. All right, if it's already out in the range here, this is you've already said it's in the range, so you don't need to say it again, right? Or you're looking at the mapping. If you want, you can say, anything in the range is going to be any element in this second set that actually depends on an element in the first set, which is 3, 4, and 13. All of them are at the end of an arrow. All right. So again, set, little braces, and the numbers 3, 4, and 13 belong to the range. Wonderful. And that's it. That's as simple as that I can get for a nice simple set of ordered pairs or a mapping. Very easy to identify the domain and the range in that case. Okay, now in the next example I have, I'm again going to be asked to state the domain and the range of the relationship shown, the relation that's shown. But this is another way to represent a relation. We can do it as a set of ordered pairs, we can do it as a mapping like this, or as a graph, right? Especially when the relationship is between one set of numbers and another set of numbers, right? So the x-axis, this is on the xy plane here, right? The horizontal axis, the x-axis, represents one set of numbers, right? Where one set of numbers can come from, and the vertical axis, the y-axis, represents another set of numbers where that second set can come from. and every ordered pair, right? I see I've got 1, 2, 3, 4, 5. I've got 6 ordered pairs plotted, 6 points plotted, right? Each one of those is an ordered pair, you know, demonstrating to me a relationship between these sets of numbers. So I'm going to label these points. We're going to figure out what these ordered pairs are. So I've got 2 for the x, you know, 3 units up. Every single notch here is a unit. Sorry, it's a hand. I drew this by hand. You know, so it's not perfect. I didn't use a ruler or anything. If you want to use a ruler or some graph paper, that'll make things look a little nicer. Perhaps I should have done that, and I apologize. But 2 units to the right, 3 units up on the y. So this ordered pair up here, this point up here, is the point 2, comma 3. All right, 2 for the x coordinate, 3 for the y coordinate. This ordered pair over here, you know, is -1, you know, on the x, 2 on the y, so -1, comma 2 for that ordered pair, that point that's plotted. This point here, you know, -2 for the x, 0 for the y, right? It's on the x-axis in line with 0 on the y-axis, so -2, comma 0. This point, -1 for the x, -2 for the y, -1, comma -2. This point, 3 on the x, and then again it's on the x-axis, so it's in line with 0 on the y, so 3, comma 0. This point here, 4 on the x, and -3 on the y, 4, comma -3. Alright, so here I have again a third representation of a relation. There's a graph. Alright, but as I mentioned before, if there's a nice, you know, finite number of points, like here there's only 6 relationships, right, 6 ordered pairs, then if you wanted to, you know, I could represent it in the other ways that we've seen. I could represent this relation as a set of ordered pairs, simply, without the graph, without the big axes. Right, as a set of ordered pairs, you know, I've got the -1, 2, and the 2, 3, and the -2, 0, and the -1, -2, and the 4, -3, and the 3, 0. Right? And there's another way. This picture, this graph, and this set of ordered pairs I have just drawn represent the same relation. Right? They mean the same thing. They say exactly the same stuff. So you could also do that, or a mapping. Right? So again, I'm going to try to draw this pretty quickly. So on the left, you know, in one box, I've got all the numbers that are the inputs, right? The first coordinates of the ordered pairs, or all the x coordinates used in the points, if you want to think of it that way. Right? So, you know, -1 is there, 2 is there. Now, some people like to put these in order. It really doesn't matter. But I've got -1 again. Sorry, oops. I've already used -1. No need to write it again. +2, -2, -1, +4. There we go, and +3. Right, so there's, you know, these 5 values in this set, and then on the other side, right, another little box with the values in the second coordinate, right, the outputs, or the y coordinates, right, if you're thinking of the graph, the y coordinates of the points that are actually plotted, which I'm seeing are, you know, +2, +3, 0, -2, -3, and, you know, 0 again. Again, I don't need to write 0 again. And then some arrows to indicate the relationships. I'm seeing -1, you know, the order pair -1, 2, -1 corresponds to 2, or 2 depends on -1, but there we go, -1 to 2, 2 to 3, -2 to 0, -1 to -2, so you got -1 up here again on the left side to -2. Right, so you see how there's 2 arrows coming off of -1, totally fine for a relation. 4 to negative 3, and 3 to 0. So 3 down here to, and then you see we have 2 arrows going to 0 on this side. It doesn't. In a relation between two sets, you can have as many arrows coming off or going into any of the elements as you wish, all right, as are dictated by the actual picture, the actual graph, or set of ordered pairs. All right, so you got a set of ordered pairs, you got a graph, you got a mapping. All three of these things represent the same relation. They mean the same stuff. Okay, so you probably see it in my mapping. Yeah, again, you probably saw it from the very beginning, but let's identify the domain and the range of this relation. All right. So the domain of the relation, again, the domain is just simply the set of the inputs, right? All the x coordinates of the points on the graph, or all of the x coordinates, or the first coordinates of the points in the set of ordered pairs, or all the elements in this first set that actually have an arrow coming off of it, at least one arrow coming off of it, and that would be -1, +2, -2, +4, and 3. All right, +3, and that's it. Those 5 values. All right. Now again, I'm not repeating -1. Right. If you mention it once, it's fine. So there's the domain, all the inputs, all the values in the first set that correspond to a value in the second set, and then the range. Remember, the range is again the set of outputs, all the y coordinates of points on the graph, or all the second coordinates or y coordinates of points in the ordered pairs, in the set of ordered pairs, or if you draw a mapping, all of the values that are in the second set that actually depend on a value in the first set that are at the end of an arrow. And those would be the +2, the +3, 0, the -2, and the -3. Right, those 5 values there. Again, you can see them in all these: the graph, the set of ordered pairs, and the mapping. All right. Again, hopefully very easy to identify when there's only a finite number of ordered pairs, when there's only a finite number of points plotted. Now I keep saying that because again, you're going to be seeing relations that have infinitely many ordered pairs quite often. So that's what my last couple of examples are on. So stating the domain and range isn't going to be a simple list like this, where you just list 5 numbers, there are going to be infinitely many numbers in the domain and infinitely many numbers in the range, so you can't possibly list them all. I've done this in a previous video, and again, if you want to look it up, please, or read in your book on the subject. When you're writing a list of infinitely many numbers, you can either describe it in what's called set notation, or write, again, I put up a video on this, interval notation. Right? Interval notation is a way to describe infinitely many numbers. So if you're unfamiliar with that, hopefully this refreshes your memory. If not, look up a video on interval notation, or read something in your book about it. I'm sure your textbook has something. Look on the index for interval notation. Alright, so here I have a picture. Right, I'm asked to identify the domain and range of the relation from, again, it's a graph, right, just like the last example, only in the last example there were only 6 ordered pairs, right? There were only 6 points plotted. But look at this graph, right? Now I pointed out some special points, right? Yeah, there's 4 ordered pairs labeled, right? There's -2, 0, there's 1, 2, there's 4, 0, there's 1, -2. Sure, there are only 4 points that are labeled, but there's still more to the graph, right? You see this like little oval shape, this ellipse, and all this light blue here. Every single one of these is a point, right? So this graph has infinitely many points on it. I'll put that off to the side. Infinitely many points on this graph. So that's a big problem, right? Well, not really. We'll see how to get around it. But I cannot write this then as a set of ordered pairs like I did in the previous one. I would maybe, if I was writing a set of ordered pairs, I'd put -2, 0, 1, 2, 4, 0, -1, 2. But then what about all these other ones? Right? There's no way I can list all of these. There are too many to count. It's infinite. Alright, so I'm not going to write this as a set of ordered pairs. And the same thing goes for a mapping. I'm not going to make a mapping where, in the left box I'd have -2, I'd have 1, I'd have 4, I'd have, now I wouldn't write 1 again. And then in the right box I'd have 0 and 2 and -2 and all the second coordinates. But again, that's just for these points. What about all these other ones, right? That make this oval shape, that make this ellipse. What about them? There's infinitely many of them. I cannot possibly list them all. What about this point here that has a x-coordinate of 1.9? Or this coordinate, these points that have an x-coordinate of 1/2 or 3/4 or -1.25. There's no way to do it. There's no way to do a set of ordered pairs. There's no way to do a mapping when there are infinitely many points. Okay. So in that case, when there are infinitely many points, I'm going to state my domain and range in interval notation. Or set builder notation, right? And I'll show you both. Okay, so for the domain, again, you're looking, I'll tell you, you just look, you're looking at the x-axis of your graph. Look at x values, right? You're looking at the x-axis. Sorry if that's a little faint. Look at x values. So look at the x values. Look at the x-axis. You see how, -2 is in the domain, right? -2 is an input, a first coordinate. So is -1, right? See, -1 is an input for this point and this point. 0 is an input for this point and this point. 1, 2, 3, 4, right? But then after 4 there's nothing, right? There's no graph over here after 4. Same thing to the left of -2. So I see -2 is in the domain, -1 is in the domain, 0 is in the domain, 1, 2, 3, 4. All those integers are in the domain, but also everything in between, right? -1.5 has points that it's an input for, right? -1/2 is in the domain. 1/2 is in the domain. 1.5, 2.5, 3.5. All those have points that correspond to it. All those are also inputs of some ordered pair, some point on this graph. So all those belong. And can you see, hopefully, that every single value between -2 and 4 is in the domain? So I'll write this out in words first. Right? So we have every value, right? Every number, every value between -2 and 4 are an input for some point, right? Are the x-coordinate of some point on this graph. Also including -2, right? We see -2 is an input here, and including 4. 4 is an input there. So including -2 and 4. All right. So the way I would write that, again, you can do two ways. One is called interval notation, where how do you represent every number between -2 and 4 that also includes -2 and 4? So you put your left endpoint, the farthest left value that's in the domain, -2, comma, the right endpoint, the farthest right value that's the end of the domain here, which is +4, and then you cap it off. And if you, again, please look this up. I'm not going to go into a whole nother, this video here, the whole thing on interval notation. So this means every number between -2 and 4, and then on the ends, you cap it off. And to say that -2 is in the domain, is included, we cap it off with a rectangular bracket, like that, little 90-degree angles here. That implies that -2 is in the domain. If it isn't, right, if there was some open point there, if it wasn't involved, if -2 wasn't in the domain, I'd put a parenthesis. Okay. And we also see that 4 is in the domain. 4 is an x coordinate. So same thing on the other end. You cap it off with a rectangular bracket. So this, again, this is called interval notation here. And that is an interval on the x-axis when you're talking about the domain, right? The x values that are being inputs in this relation, right? That are x coordinates on the graph. Now you could also do what's called set builder notation. So or, and then I put little curly braces, right? It's a set builder notation. And what I'm doing here is I'm stating all the values of x that are used as inputs in this graph, all the x coordinates in this graph. So since we're talking about values of x, I'll put that letter there, right? I'm talking about all values of x, and then a little bar or a colon sometimes. You might see two little dots, but I like a little bar. So it's the domain is all values of x such that, and then after the bar comes a description of the numbers in your set. What are these values of x? Well, they're all the values of x between -2 and 4, so a little inequality here, that are greater than -2 and at the same time less than 4, right? All the values of x between -2 and 4 and including those, right? So a little less than or equal to, right? So that way -2 and 4 are included. And again, I have put up a video on interval notation where we go back and forth between writing an inequality and the interval that represents the same numbers as that inequality. Alright, so these mean the same thing. These are the same numbers, and this guy here is likely referred to as set builder notation, where I'm just describing all the numbers that I'm that are in this set after a bar. So it's all the x coordinates, all the values on the x-axis that are or such that they're between -2 and 4 and including -2 and 4. Alright, so these are the same numbers. Alright, and the same thing goes for the range. Alright, so the range, again, there are infinitely many points graphed on this plot. So I can't possibly list them. I can't put them in a set and list them all. I can't make a mapping. There's infinitely many is too much. Now I'll describe it in words. Alright, I'll describe it in words first. So look, now the range, right? For the range, you are looking at the y values, right? You look at the y-axis. Right. So I'm looking from, again, when you're writing interval notation, you always go low to high. So I went from left to right on the x-axis. For the y-axis, I'm going, bottom up, right, from bottom to the top. Those are low numbers to high numbers. All right, so looking at this now, we're just looking at the y coordinates now. Going from bottom to top here, you see the lowest point on this graph has a y coordinate of -2, right? So it looks like -2 is in the range. Is a y coordinate is an output, right? The range is a set of the outputs. We see that 0, right? 4, 0, -2, 0. 0 is in the range. It's a y coordinate for these 2 points. And the highest point on this whole graph is 1, 2. So 2 is in the range. So -2 is in the range, 0 is in the range, 2 is in the range from these 4 labeled points. But can you see also that -1 on the y-axis here is in the range, right? There's this point here and this point over here that have a y-coordinate of -1. +1 is in the range, right? There's this point over here and this point over here that have a y-coordinate of +1. So -2, -1, 0, 1, 2, all those numbers are in the range. But can you see also that everything in between those, not just the whole numbers, not just the integers, are in the range? You know, -1.5 has these 2 points where it's a y-coordinate. You know, +3/4 has these 2 points, you know, where it's a y-coordinate. Everything from -2 to +2, including -2 and +2, are in the range, right? Our y-coordinates. So I'm going to write that in words, right? Every single value between -2 and +2 I'll just say inclusive, all right, to indicate that -2 and +2 are also in the range. That's a word description of the range. And then I'll do the same thing I did for the domain, right? We'll write this word description in interval notation. So how do I indicate, you know, every value between -2 and +2? So that's, you know, -2 left end or bottom end to top. You know, you go left to right for x-axis, go bottom to top again for y-axis. So -2 to +2. So I put -2 comma +2, meaning, you know, indicating that every single number in between these two is in the range, is a y-coordinate of some point on the graph. And then to indicate again that, you know, the endpoints, the -2 and the +2, are also in the range, the rectangular bracket. Right, that indicates that -2 is in the range, and again the rectangular bracket indicating that +2 is in the range. So you could say that this is the range in interval notation, or again that set builder notation, little curly braces here. Now this time we're talking about y values, right? Values on the y-axis. So instead of the variable x, I put the variable y, and then a little bar or a colon, and I'm saying like the range of my relation here is all the y coordinates, all the values of y, such that, you know, and then I'm just going to take this interval notation and write it as its equivalent inequality, but using y instead of x, right? So it's all the y values between, right? So greater than -2 and less than +2. All the y values between -2 and +2, and also including those, right? So the little or equal to symbols there. Right, just writing that interval notation as its equivalent inequality. Right, this notation and this inequality represent the same numbers. Okay, wonderful. So again, a little tougher, right? Maybe a little trickier to think about. But when a relation has infinitely many ordered pairs in it, infinitely many relationships, you're not going to be able to list them all. You're most likely going to have to state your domain and range in one of these notations, you know, to indicate that there are infinitely many values. You know, everything from -2 to 4, including -2 and 4, make up the x coordinates. You know, all the inputs, they make up the domain, and every value from -2 to 2, including -2 and 2, make up all the y coordinates. All the outputs, you know, all the second values make up the range. All right, so I've got just one last example for you, where again we're going to look at a relationship between two sets of numbers, a little graph, set a bunch of ordered pairs where there are infinitely many, right, and that's this graph here. Right, just a nice straight line, a nice linear graph. So again, you got x-axis, y-axis, you know, two sets of numbers. This is a relationship between two sets, and they just happen to be sets of real numbers this time. Now, yes, there are two, you know, special points that I've pointed out. You know, sure, there's this point here with -2 comma 0. There's this point over here with, you know, 0 comma -1. But those aren't the only 2 points on the graph. Every single point on this, you know, this light blue here, this line, is part of the graph, is part of the relation. And notice the little arrowheads at the end. This indicates that this is going this way, you know, forever, and this little arrowhead indicates that the graph is going this way forever, right? I just can't draw it. I mean, if you want to continue it, fine, just say, hey, this is doing this all the way off the page, and this is doing this all the way off the page, forever and ever and ever without end. All right, so again, I'm asked to state the domain and the range. Now the domain, this time I'm not going to write them out in words, I'm just going to say it in words, and we'll put it in that because there are infinitely many values here. Again, I'm kind of resorted to putting the domain and range in interval notation, or the set builder notation. Alright, so for the domain, again, I'm looking at x coordinates. I'm looking at the x-axis, x values that are used as inputs in the ordered pairs of this relationship, this graph. So yes, there are these two special points that I've labeled. -2 is in the domain, 0 is in the domain, right? But you see how -3, -3 is in the domain, right? There's a point with an x-coordinate of -3. -4 is in the domain, -5, -6, -7, -8, -1, 0, 1 is in the domain, 2 is in the domain, 3 is in the domain, 4, 5, 6, 7, 8, blah, 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 and everything in between, right? 2.5 is in the domain. There's a point with an x-coordinate of 2.5. 3 3/4, pi, right? A little about 3.14. Everything in between too, not just those integers, not just the whole numbers, is in the domain. And it looks like everything on the x-axis actually, right? Because of the graph going up this way forever and down that way forever. Every x value I choose, any x value you think of, has some point on this graph where it is an x-coordinate. So the domain here is all real numbers. Remember, the x-axis represents the set of real numbers. So to indicate that, right, I guess you could write it in words. I know I said I wouldn't write it in words, but it's a short phrase. Just all real numbers. Right, so anything you can think of on the x-axis is in the domain. Now, if you write this in interval notation, remember I'm going left to right. Remember, low to high numbers. There is no lowest value in the domain. Right, there is no left end. Right, this goes on this way forever. Like there was in the last example. In the last example, the lowest value in the domain was clearly -2. Again, if you want to look at my video on interval notation, or look it up in your books, or find other videos, remember, when there's no lowest value, they indicate that with -infinity, right? And a comma, that's your left end. Again, this is not a number, right? -infinity is not a number. It's an idea, it's a concept that just means there's no lowest value in the domain. You pick a value, -100 isn't it? I say, well, what about -101? You say -1,000,000. Well, what about -1,000,001? -1 billion, and so on. So there's no lowest end, no lowest value in the domain. And same thing for the upper value, right? The right part, the second part of this interval. There is no highest value in the domain. You go to 1,000, I say 1,000,000. You go to 1,000,000, I say 1,000,000,000. Has a point where it's an x-coordinate. So to indicate that there's no highest value in the domain, put the positive infinity symbol or just the infinity symbol. Great. So this -infinity, infinity indicates that all real numbers are in the domain. And then again, we cap, and of course for these intervals you got to cap them off with either a parenthesis or a square bracket. Well, I said a second ago, these are not numbers, right? Infinity is not a number. It's a concept, it's an idea. So because it's not a number, it's not actually a number in the domain. So because they're not part of the domain, we indicate that with parenthesis, right? So you always put parentheses on infinity, or to cap off infinity or -infinity, right? So this here again indicates that the domain is all real numbers, this interval from negative infinity to infinity. Now if you're doing that set builder notation, you could also do this little set, and we're talking about x coordinates, right? So put the variable x in the little bar. The domain is made up of all x values such that, and then I'll just just state simply x is a real number, or x is real, and then close it, right? Just again a little after the bar, just a little condition on the variable to tell you, what numbers actually belong in this set, and this would indicate to me that any real number at all belongs to this set, and that's what the domain is, right? It's all real numbers. And hopefully you can see that it is very similar for the range. Right? Again, the range, you're looking from bottom up, right? Low y values to high y values, looking at the y-axis. And the same thing, yeah, there's these two special points. 0 is a y-coordinate of this point, so 0, y value 0, is in the range. -1 is the y-coordinate of this point, so -1 is in the range. But can you also see that +1 on the y-axis, that is a y value of this point? +2 is a y value of this point, +3 is a y value of this point, and no matter how high up I go, right, because this line goes up, 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 up this way forever, no matter how high up I go on the y-axis, there's going to be some point way out here, way out to the left, that has that as a y-coordinate. Same thing for going down. -2 is a y-coordinate of that point, pardon me, -3 is a y-coordinate of that point, -4 for that point, -5 for that point, and because of this line going down this way forever, no matter how low I go on the y-axis, there is some point way out to the right, that's going to have that as a y-coordinate, and everything in between as well, not just the whole numbers, not just 1.5 is a y-coordinate here, -3/4 is a y-coordinate here, -square root of 2 is a y-coordinate here, and so on, right? So it looks to me again like every real number. Remember the y-axis, just like the x-axis, the y-axis represents all real numbers. So again, for this picture, for this graph, this relation, the range is all real numbers. And as indicated before, that means this is our interval. Or if you want to write it in interval notation, know that there is no lowest value in the range. Right? You say -1,000, I say -1,000,000. What about -1,billion? Negative Google. So I indicate that with -infinity, comma, and again there's no highest value, no largest value in the range. So we indicate that with a positive infinity. And again, infinity, -infinity are not numbers, so they don't actually belong to the range. We indicate that by capping those off with parentheses to mean that they don't belong. Alright, and then so you can write all real numbers, you can write this interval, or you can write in that set builder notation. Now remember, we're talking about y coordinates here, so values of y such that y is real. Just a simple little description of all the values of y that are actually belonging to the range, that are actually y coordinates or outputs for points on this graph. Great. So there you go. Alright, so then obviously other examples will come in the future, but for right now, just know that if you have a finite number, a nice small number, easy to count number of points, you can represent that relationship, those relationships, as a set of ordered pairs, as a graph, as a mapping, very easily, and it's very easy to state the domain and range in those cases. But when your relation, has infinitely many ordered pairs, like this line, or that oval shape, that ellipse from the previous example, it's a little trickier, right? You gotta know that there's infinitely many ordered pairs, so I can only really represent them with a graph or an equation, right? We haven't really seen an equation yet in these past couple videos on relations. We'll get to that soon, most likely the next video after this. Talk about representing a relation as an equation, an equation describing the relationship between the two variables, like y equals 3x plus 1 or something. But if a relation has infinitely many ordered pairs, chances are you're going to have to state the domain and range as an interval of numbers, right? Like in the last two examples, or in that set builder notation, describing, with an inequality or a little verbal description, just a description of all the infinitely many numbers that belong to the domain and range. Okay. All right. And as I like to say at the end of these two, just try your best, do the best you can to try to understand the material on your own before you go looking for help. If you're, please, read the material, read the author's examples, perhaps even sometimes try to work out the solutions to an example before you read how the author did it. See if you can learn from your mistakes there. Of course, practice exercises, practice problems, and for certain ones you'll probably be able to look up answers to be able to check yourself, see how you're doing. And don't just give up after the first try. Don't get so easily frustrated. If after several attempts at a problem it's still not clicking, still not working for you, go back and read the material again. Maybe even a third time, because maybe on that second, third read through, you'll see something that you didn't see the first time, or something will make more sense because of the fact that you've been practicing problems, or that you just didn't catch. Something will make more sense the second or third read through that didn't the first time. But if after that, if after several read-throughs of the material, several attempts at problems, you're still not getting it, it is not a sign of weakness whatsoever to go looking for help. Ask for help. That is what other people are there for. So ask a teacher, a tutor, a friend of yours who or someone else in the class that knows the material well and is willing to help. Look for supplemental materials online on the subject. Look for videos on the subject, maybe such as this one, or ones out there that are plenty better than this one. I assure you, you can find them. And just keep at it. Stay persistent, keep practicing, and try to have a positive attitude. That makes all the difference as well. Don't just go into something thinking you're going to hate it, because you're probably just going to keep hating it. Go into this with an open mind, thinking I'm going to learn something, I'm going to enjoy learning it, and just stay positive about it. And it's amazing the difference that can make. So keep practicing, stay persistent, stay positive, and try to have some fun. And thank you for watching.